here, I take K sample and I have a joint probability density of that. And taking that, the sum of those K sample, if I shift the whole thing over here, if I add a constant to all of them, that is the same. Right, so you see that. So that thing here is equal to f of x of n1 plus some constant m here, x of nk plus some constant m. Okay. And this is for all m and 1. Okay. So you see that what I described in word that exactly the formula. Okay, so that is the behavior of the signal in the statistical modeling doesn't change with time. Okay? Alright. I know it's a difficult concept, but let's see. And even that description is still a little bit too much to use, so now we move to an even simpler, because here's what happened. The signal we have, so maybe we'll draw out the signal. So the signal here, and here's the n. And remember now, in every instant of time, I have some value. Again, thinking about it is I'm recording the noisy signal for about 5 seconds. And then another 5 seconds, I record another noisy signal. So every time I record, I get something coming out like this. And I described a little bit using a random process. Now, the signal processing we don't need to use that much. But I'm going to describe them now is two things I need to specify. First is I want to specify a single random variable. I want to specify one at a time. And the other thing is I want to specify the joint density function of two random variables. Right? So I take any kind of signal and I want to see. And the definition here, another definition of random process. A random process is y stationary. Okay, so WSS. It is a y stationary process. It is a y stationary process. So for engineering we need to use two things. If I take this expectation, okay, so you see I'm going to use mix, so maybe it is this n. If I take the expectation of this, maybe we start practicing using, no, not okay. And if I take the expectation, so inside here is a random variable. It is a random variable, okay. So random variable, I take expectation of a sample at location n. Okay, so remember each of them not a one value, but a whole collection of them, a sum of them with random variables. But this thing here is stationary because you see this thing here, as we said, the distribution functions are the same. Doesn't matter where I put it. Right? But now I'm saying that if that's the case, and of course this thing here must be a constant. Right? But this will put a constant and I can define that equal to mx. So it doesn't depend on n. It doesn't depend on n. It is equal to a constant which is only dependent on the whole signal. Okay. Of course, stationary implies this. Second, the expectations of x n and x of n minus n. Okay, so maybe I should use this thing here is mu. And taking the expectations of x and its n sample previously. So I take A2 this, and you see that if the signal that is y stationary, I take A2 random variable here, they have some joint probability density function. And this function is the same for these two samples, the same for these two, the same for these two, and so on. So it's the same for everywhere. Right? So now we call that, so it is a function now, I call this gamma of x of n. So this, of course, doesn't depend on n. So it's the same anyway. It's only depend on the distance of these two samples. So obviously, a stationary process implies these two. But for signal processing, we need to assume only these two. Right? Also only these two. So this is much wider set. But that is good enough for us. So if a random process is a y-sense stationary process, it is satisfied these two conditions. Okay? Still with me? Alright. So now let's put them more. So now we start moving into signal processing and see. So now we have to do a simple exercise. Simple exercise. By the way, this we call first order statistics, and this is obviously second order statistics. Second order statistics, right? Maybe we should also define. So now if I also have, let's see, if I now have not just one signal, I not just have one signal. You see this thing here, I take one random variable with another random variable of this. Now maybe I want to put not just one signal, I want to take the signal x and then the signal y. Right? Signal x and signal y. And each of them are random variable. Each of them are random variable. Each of them are not random, sorry, random processes. So these are two random signals. Two random signals. And we want x and y is joint y-sense stationary if now if I were to define the expectations of x and y of n minus n, and this thing here is, so taking this, so I have a random variable that depends on n, a random variable that depends on n and n, and this thing now is only a function of x, y, so some function, but it only depends